Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're on Chapter 8, 8.4, and we'll be considering tangents to polar curves. Given the polar curve, r equals some function of theta, we learned in a previous lesson that the Cartesian coordinates of any point on the curve are x equals r cos theta and y equals r sine theta. But if we choose to substitute f of theta for r, then we can write the curve as x equals f of theta cos theta and y equals f of theta sine theta, where f of theta will just be whatever function we're given in the question. To find the gradient at any point, we can now differentiate, and dy by dx will equal dy by d theta divided by dx by d theta. And you may be asked to find dy by dx, but more frequently it is only dy by d theta or dx by d theta you're asked to find for the sort of questions we most frequently meet in A level. Now, one application of tangents which can be of help is in sketching curves. So if we consider the rose curve with equation r equals 2 sine 3 theta, 3 is an odd number, so there'll be 3 loops, and it looks something like that. In general, if r tends towards 0, as theta tends towards the angle alpha, then the half-line theta equals alpha will be a tangent to the curve at the pole or at the origin. So for the rose curve above, the half-lines theta equals 0, which would be the positive x-axis, that will be a tangent to the curve. As you can see, theta equals pi by 3 would be the line at the top of that first loop. Theta equals 2 by 3 would be this line. Theta equals pi is the negative x-axis. Theta equals 4 by 3 would be here, and theta equals 5 pi by 3 down here. All of those lines are tangents to the curve at the origin, at the pole. Okay, coming back to where we were just now. Another particular use is in finding tangents which are parallel or perpendicular to the x-axis, to the initial line. So given the polar curve, r is some function of theta, we've just said we can write x as a function of theta times cos theta and y as a function of theta times sine theta. Dy by d theta equals 0 will give any tangents which are parallel to the x-axis, to the initial line. And dx by d theta equals 0 will give any tangents which are perpendicular to the x-axis, the initial line. So for example, for the cardioid r equals 1 minus cos theta, find the coordinates where the tangent to the curve is parallel to the initial line. Parallel means we're going to be finding dy by d theta, and we're going to let dy by d theta equal 0 and then solve that equation. And y is f of theta times sine theta, where f of theta is 1 minus cos theta in this question. Okay, I'll let you have a go at working your way through this yourself. So pause the video, see if you can make sense of all of this, and then come back to me when you're ready. Okay, let's have a look. So we'll be using y equals f of theta sine theta because we want the tangents which are parallel to the x-axis. F of theta in this question is 1 minus cos theta. Multiplying out the brackets gives us that. Differentiating with respect to theta gives us cos theta minus cos squared theta plus sine squared theta. And then writing sine squared as 1 minus cos squared will give us that. Collecting all the terms together gives us that. Now we want to know when dy by d theta is equal to 0. Well, just rearranging that will give us 2 cos squared theta minus cos theta minus 1 equals 0. And factorizing that gives 2 cos theta plus 1 times cos theta minus 1 is equal to 0. And either the first bracket will equal 0, which gives us cos theta equals minus a half. And if cos theta is minus a half, that will give us theta equals 2 pi by 3 or minus 2 pi by 3 radians. If theta equals 2 pi by 3, just substituting into the equation for r, will give us r equals 3 over 2. And similarly, if theta equals minus 2 pi by 3, again, we get r equals 3 over 2. Now we can need to consider the second bracket equals 0. So if cos theta minus 1 is 0, that means cos theta equals 1. That will give us theta equals 0, or 2 pi. And in both cases, we get r equals 1 minus 1, which is 0. Therefore, the tangents parallel to the initial line are at the points 3 over 2, 2 pi by 3, 3 over 2 minus 2 pi by 3, 0, 0, and 2 pi 0. Now, these last 2 points are the same as each other, but you can't assume that they would be. It isn't necessarily the case that 0 and 2 pi will give you the same coordinate. If we have a quick look at the curve, we can see where these are. So this first point, 3 over 2, 2 pi by 3, will be up here at the highest point on the cardioid, where the tangent to the curve is parallel to the x-axis. The second point is the point opposite that, at the lowest point on the curve, where again the tangent is parallel to the x-axis. Both of these are the same point. The line here, well, this point and the half line would be the x-axis itself. And that would be the tangent. Okay, example 2. Sketch the curve of r equals 4 sine 3 theta for theta between minus pi and plus pi, and then find any points on the curve where the tangent is parallel again to the initial line, either by using sine 3 theta equals 3 sine theta minus 4 sine cube theta or otherwise. Now, you've been given a trig identity here, and what they're saying is the easiest way to do the question is by using this identity, but you're welcome to try any other method if you want to. Okay, I'll let you have a go at working your way through this. So pause the video, have a go, and then come back to me again as soon as you're ready. Okay, let's have a look. So r equals 4 sine 3 theta. That's a sketch of the curve. That is what it would look like. And it's important to note that as with all rose curves, they're only defined some of the time, or at least that's sometimes the case. In this instance, we've got a petal here from 0 to pi by 3, and then there's a region where the curve is not defined. And then between 2 pi by 3 and pi, the curve is defined again. Then the region isn't defined. It's defined between minus 2 pi by 3 and minus pi by 3, and then it isn't defined again. Now, that will matter later on when we're considering values of theta, and which we do have to include and which we can't include. Okay, part 2 asks us to find any points on the curve where the tangent is parallel to the initial line. So again, we'll be using y equals f of theta sine theta. In this case, f of theta is 4 sine 3 theta. And this is the moment when we need to use the trig identity in order to help us differentiate the function. So sine 3 theta is equal to 3 sine theta minus 4 sine cubed theta. Multiplying out the brackets will give us that. Differentiating that gives us 24 sine theta cos theta minus 64 sine cubed theta cos theta. And factorizing that gives us 8 sine theta cos theta into 3 minus 8 sine squared theta. To find where the tangents are parallel to the initial line, we need to know when this equals 0. So that is what we will be solving. And that gives us various possibilities. Either sine theta equals 0, or the second term, cos theta, could equal 0, or the third term, the bracket, 3 minus 8 sine squared theta equals 0. And we do need to consider each of those separately. That's what the curve looks like. Now, if sine theta equals 0, then theta either equals 0 or theta equals pi. Theta equals 0 will give us the tangent here, the positive x-axis. Theta equals pi will give us the tangent on the other side, the negative x-axis. So when theta equals 0, r equals 0, which implies that dy by d theta equals 0, first of all, where r is 0 and theta is 0, and secondly, where r is 0 and theta is pi. We now need to consider what happens if cos theta equals 0. That gives us two possibilities. Theta is pi by 2, or theta equals minus pi by 2 radians. Now, r is not defined when theta equals pi by 2. Pi by 2 is 90 degrees, and that would be up here, where the curve is not defined. However, when theta equals minus pi by 2, there's no problem. The curve is defined, and r equals 4, which implies that dy by d theta equals 0 at the point where r is 4 and theta is minus pi by 2. And you can see that if you drew the tangent at that lowest point on the curve, it would be parallel to the x-axis. The last possibility was if the bracket 3 minus 8 sine squared theta is equal to 0, which gives us that sine theta is either plus or minus the square root of 3 divided by 8. First possibility is sine theta equals plus 3 over 8, which gives us theta equals 0.66 radians, or theta equals 2.48 radians. Now, first of all, if theta equals 0.66, substituting into the formula for r gives us r equals 3.67, which means that dy by d theta equals 0 when r is 3.67 and theta is 0.66 radians. That point is this point here, at the very top of the first petal. And again, at the very top of that, if you drew the tangent, it would be parallel to the x-axis. When theta equals 2.48 radians, again, we get r equals 3.67 when we substitute that into the equation for r. And that gives us dy by d theta is equal to 0. At 3.67, theta equals 2.48 radians. And that point is the point of this, the highest point on the second loop. And again, it's fairly clear to see that at the very top, the tangent will be parallel to the x-axis. When theta equals minus the square root of 3 over 8, theta either equals minus 0.66 radians or minus 2.48 radians, and both of those are in the region which is undefined. The first in this region here for minus 0.6 radians, the second in the region over here for minus 2.48 radians. So r isn't defined for either of those, which means that the tangent to the curve is parallel to the initial line at those 5 points, 0, 0, 0 pi, 4 minus pi by 2, r equals 3.67 and theta equals 0.66 radians, and r equals 3.67 and theta equals 2.48 radians. It is also worth noting, as we sort of hinted at just now, that one use of this, and it does turn up in questions this, we can use y equals r sine theta to obtain the maximum values of the function in the y direction. Now, the minimum value is easy to see by inspection. The minimum value is down here at minus 4. So minus, r will equal 4, and theta will equal minus pi by 2 radians down there. But these 2 points here, that's where you would get the maximum value in the y direction, and they will be these points here at 3.7, 0.66, and 3.67, 2.48. Substituting those into y equals r sine theta, we can find the y coordinate. And you get 2.25 in both cases. And those will be the 2 points where you get the maximum value for y. It's worth remembering that. Okay, example 3. Given r equals 6 sine 2 theta, find the points where the tangent to the curve is perpendicular to the initial line, and then find in polar form the equations of those tangents. Okay, this time we are going to be using x equals r cos theta and finding dx by d theta. I'll let you have a go at that, and I'll let you have a go at seeing if you can work out what the polar form of the equations of the tangents is. So pause the video, try and work your way through this, and come back to me when you're ready. Okay, let's have a look. So r equals 6 sine 2 theta. Now 2 is an even number, so we have to double that, and we get 4 separate loops for that particular curve. That's what it'll look like. Now we're only considering the values of theta between 0 and pi by 2. So actually we would only get this very first loop here, up in the first quadrant. These are the 3 loops are outside of that range. So we are only considering the first loop. Find the points where the tangent of the curve is perpendicular to the initial line. We'll just go back, and the tangent's going to be perpendicular at two places. So you can see the curve gets steeper and steeper as we go in towards the origin here. So at that point, we'll have a vertical tangent, and also here we'll have a vertical tangent. So that is what we're looking for. X equals f of theta cos theta. F of theta is 6 sine 2 theta in this instance. Substituting in gives us that. Sine 2 theta, the trig identity for that is 2 sine theta cos theta, and that will help us differentiate. So we get x equals 12 sine theta cos squared theta. Differentiating gives us all of that. Tidying that up gives us minus 24 sine squared theta cos theta plus 12 cos cubed theta. Sine squared theta is 1 minus cos squared. So substituting that in, we'll get everything in terms of cos theta, which always helps when you're trying to solve an equation. So we'll get 36 cos cubed theta minus 24 cos theta is equal to dx by d theta. We need to know what happens when that equals 0. Factorizing that will give us 12 cos theta into 3 cos squared theta minus 2 equals 0. And then either cos theta equals 0 or the bracket 3 cos squared theta minus 2 equals 0. If cos theta equals 0, that'll give us theta equals pi by 2 or theta equals minus pi by 2. And at this point, we do need to remember that they've limited the domain to between 0 and pi by 2 radians. So theta equals minus pi by 2 is outside of that given range. But if theta equals plus pi by 2, then r equals 0, if we substitute into this, which means dy by d theta is equal to 0 at 0 pi by 2 radians. If 3 cos squared theta minus 2 equals 0, that means that cos squared theta equals 2 over 3, and cos theta equals plus or minus the square root of 2 over 3. If it's equal to plus the square root of 2 over 3, then theta either equals 0.62 radians or minus 0.62 radians. When theta equals 0.62, substituting into r gives us r equals 5.66, which means that dy by d theta equals 0 at r equals 5.66, theta equals 0.62 radians. Cos theta equals minus the square root of 2 over 3, then we get theta equals 2.53 radians, or theta equals minus 2.53. Both of these values are outside of the given range, which is from 0 up to pi by 2. So we can ignore those. So dy by d theta equals 0 at this point and this point. Both of these, therefore the tangent of the curve is perpendicular to the initial line at those 2 points, 0 pi by 2 and 5.66, 0.62. Okay, we now need to find in polar form the equations of those two tangents. And just to remind you where they were, there's one of them which is here at 0 and one of them which is over here on the far right. So those are the 2 points we're considering. To find the equations of the tangents perpendicular to the initial line, because we have vertical lines, in Cartesian form, the lines are very simple equations, x equals 2 or x equals 3, something like that, which means that all we actually need to find are the crossing points on the x-axis on the initial line. And then we will be able to write down the equations of the lines. So first of all, for the tangent through 0 pi by 2, so that's going to be this line here. X equals r cos theta, which gives us 0 cos pi by 2, which is 0, which is self-evident from the sketch. So this tangent here is where x equals 0. And in Cartesian form, the tangent is the line x equals 0, which is the y-axis. In polar form, that's the line theta equals pi by 2, or the half line theta equals pi by 2. Slightly trickier is working out the equation of the tangent that goes through 5.66, 0.62. Well, we want to know what the x-coordinate is, where that line crosses the x-axis. X equals r cos theta, so that'll give us 5.66 cos 0.62. So the x-coordinate at that polar coordinate will be x equals 4.61. So in Cartesian form, the tangent will be the vertical line here, x equals 4.61. What's going on in polar form? So we've got the curve, there's the tangent to the curve, and the tangent is perpendicular to the initial line, the x-axis. Those are the polar coordinates of where the tangent meets the curve. R equals 5.66 and theta equals 0.62. And then x equals 4.61 was the x-coordinate of this point. But because it's a vertical line, it will be the x-coordinate on the x-axis. To write the equation in polar form, we need to find r as a function of theta. So we want to make a right-angled triangle with r and theta shown. And then using simple trigonometry, the cosine of theta will be the adjacent side over the hypotenuse, which is 4.61 divided by r. All we need to do now is rearrange that to get r as a function of theta. And that'll give us r equals 4.61 times by 1 over cos theta. 1 over cos theta is sec theta. So the simplest way to write down the polar equation of the tangent is r equals 4.61 sec theta. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 164 and have a go at exercise 8D. Thank you very much for listening, and cheerio.